moving on to slew rate. Anybody heard of this thing right here? Slew rate. What is the slew rate? Slew rate. Okay, slew rate is defined as the maximum rate of change of an op-amp's output voltage and is given units of volts per microseconds. Important to know to get a distortion less output. In other words, how quickly op-amp reaches the peak maximum value. Okay, so I'm gonna make it very simple here. So say you have an op-amp. The positive, which is the non-inverting terminal, is connected to some input, and then this negative terminal is basically connected to the output voltage over here. And because output voltage is connected to the negative feedback, your Vn is going to be whatever the output voltage is there. And then if I say this Vn over here, this is voltage, this right here, is some peak value sine omega t. And because this is in a voltage follower configuration, what is the property of the voltage follower configuration? So you have Vp here, right? You have Vn here. Ideally, you know Vp is going to be equals to Vn, correct? If Vp is say 5 volt, then Vn is also going to be 5 volt. And because Vn is connected to V naught, so Vn equals to V naught equals to 5 volt, correct? And if I find out the gain, which is the basically ratio of the output voltage over input voltage, right? So I would basically get a unity gain because both V naught and inputs are same. So it's basically referred to the voltage follower or unity gain amplifier. Okay, so if I at the input, get something like this, a signal like this, at the output, what would I get? Yes, folks. If the input, I'm sending this signal, what would I get at the output over here? Will I get the same that I have over here because it's a unity gain? It's not being amplified. Whatever I have at the input signal, I get the same at the output, right? Is everybody following me? Okay, so this is the input in purple. So the output, what is going to happen with the output? The amount of time it takes for the output signal to follow the input signal, like reaching its maximum, this is the maximum value. That time is referred to as slew rate. So it's not going to be exactly like this. Okay, there is going to be some kind of, it's going to go like this, it's going to go like this, go like this. There's a delay here, and then therefore it's going to go like this, and there's going to be a delay here. There's going to be an offset. It's not going to be superimposing the input signal. Okay, that's what we refer to as a slew rate. And the time it takes, remember, when you have this input here, the output will slowly increase. Okay, and once it reaches this maximum value, so the amount it took from here to get to the maximum value, that's what we refer to as a slew rate. So how quickly op-amp reaches the peak or maximum value. Another thing was important to know to get a distortion less output. Okay, so say if the slew rate is higher, what do you expect at the output over here? If the slew rate is higher, what do you expect at the output?
I think the output would more closely match the input.
It's the other way. Okay, so if I have the slew rate, which is say, maybe we can look it over here. So this is the input square wave here. Okay, this is the input signal. Okay, and that's again, it's a voltage follower, so it's just gonna copy in the input signal. But the output, how output responds to it, again, when the logic goes high, it takes a little bit of time and then gradually goes up, reaches its maximum value, and then when the logic goes low here, it starts going down. So there is an offset over here, and output is limited by the slew rate. Okay, if I change the magnitude of this signal, okay, so say this was 5 volts, okay, initially. If I change it to say 3 volts, okay, which would mean I would get something like this, maybe a little better over here like this. So which one is better, the one in the blue or the one in the green? Which one is closest to the input signal?
The green one.
The green one is actually closest to the input signal because, when I reduce the magnitude over here 3 volt, that means a lot of this portion is basically, void out, right? Similarly over here, this portion is void out. And now this is a lot more closer to the blue line. And remember, because I changed the magnitude to 3 volts, so it's actually gonna go, the original signal is gonna be like this, okay? The original signal is gonna be like this. So the green line is a lot more closer to the blue line than how initially it was. So again, this is important to know because you would need to have this number, and ideally you wanted this to be as small, and this is kind of a resolution too. The LM74 IC, which is again a very popular one, that has a slew rate of 0.5 volt per microsecond. So again, let's do a little bit of analysis. Let's go into a little bit of more detail. Again, this is a voltage follower. At the input right here, I have VP sine omega t, VP sine omega t. And we know the output is going to be same also, because in a voltage follower, V naught will just basically follow whatever is over here, correct? So I can also write VP sine omega t, right? And what we have basically learned from the slew rate, it is actually the change in the output voltage over a period of time. On the x-axis you got the time, and on the y-axis you got the magnitude. So it's basically, and this is actually V naught here, so say V naught, actually this is V naught and this is Vn. So it's basically a change in voltage over a period of time. So I can write down this equation as dV naught over dt, that's basically change in output voltage over a period of time, equals to, if I take a differentiative, uh, what would this be? Vp sine omega t is equivalent to cos omega t, correct? And then cos omega t dot omega, correct? That is what we would get. And also remember one thing, this right here is equals to, our goal is to get to the peak value, right? We would get to the peak value when this cos omega t should equals to what?
1.
1, okay? So when that is 1, we get the peak value. So this is Vp dot omega. And then we know that omega is basically the 2 pi f. Okay, so if I put this equation in this equation on the left, so slew rate equals to dV naught over dt, change in output voltage over period of time, equals to Vp dot 2 pi f, and this is expressed in volts per second. If you want to convert in microvolts, because usually it's gonna be in microseconds. So all you need to do is divide it by 10 to the power 6. So you get 2 pi f Vp divided by 10 to the power 6, and this is volts per microsecond. Okay. So when it says 0.5 volt per microseconds, that means every, every 1 microseconds, it ramps up by, so say this is 1 microseconds over here, 1 microsecond here. So it will go to 0.5 and then 1 and then 1.5 and then 2. So, you have this magnitude of the output voltage, and then you have time here in microseconds. Okay, so it's slowly. You cannot exceed this. You cannot exceed this. It's constant. It's something that is internal to the chip, to the IC. Okay, so this is kind of like a introduction to what slew rate is.